videos. Okay, so again, a reaction system will shift itself in order to counteract, oppose, another word to use there, any stress, disturbance, change, okay, applied to it. It's attempting, or it will attempt, to return to the same equilibrium position if possible. Right? That equilibrium ratio, products to reactants, that's where the system wants to live. Okay, so it's going to try to get back to that if possible. Right? Now there are lots of ways we could stress or disturb a system. Okay? But to make life a little bit easier as we're learning about this, we're only going to consider the effects of two types of changes. Concentration changes and temperature changes. Okay? These will be the two categories of equilibrium stresses that we look at. All right. You can do things like pressure, you can do things like side ionic concentrations, but we're not going to worry about any of those things, fancier things. We're just going to look at these two basic ones, all right, to get us started. Let me go back to the, I'm loving this eraser analogy that we've been using. So the eraser example. All right. And let's go through those numbers again. We had me, and then we had our student. And we started with 6, 0, 5, 1, 4, 2, 3, 3, 2, 4, 2, 4. And that's when we were at equilibrium. Okay? And we had our Q, right, which was 0, 0.2, 0.5, 1, 2, 2. And so this is when we know we were at equilibrium, when the Q stopped changing and it became the equilibrium constant. Okay? So our eraser system has achieved equilibrium. Doesn't mean it stopped, remember. The student and I were still constantly exchanging erasers, right? We were just keeping our respective piles the same size. So here's how the disturbance could play itself out. We're at equilibrium. What if somebody added, let's say, 6 new erasers to my pile? So my pile jumped from 2 up to 8. Are we at equilibrium now? No. And what proves it is if we try to calculate Q. Right? Oh, back to 0.5. So we could forget about actually this Le Chatelier's principle for a second. We already know about reaction quotient. Reaction quotient tells us what's going to happen now. Our reaction quotient is smaller than our equilibrium constant. Anytime that's true, we know the forward reaction is what's going to occur to get us back to equilibrium. So what's going to happen is we're going to start shuffling this increase in my pile over to the other side. So, if I go down to 6, the other side goes up to 6. Now we're at 1. If I go down to 4, the other side goes up to 8. We're back to equilibrium now. And that's where we would stay unless another disturbance happened. Okay? All right. So this is really demonstrating the Le Chatelier's principle. The stress was to increase what we're going to call the reactants. My erasers are reactants. The student's erasers are products. Okay? And the counteracting was to then decrease my pile. All right? It was artificially or temporarily increased. So to counteract that, we brought my pile down, which consequently brought the student's pile up. All right? But the goal was to get back to the same ratio. Yeah, our two numbers are different than what they originally were, but they're in the same ratio that we had originally for our equilibrium constant. All right? So the net effect, sort of the lesson that we learned from here, is that any time a species has its amount, I can't say concentration because it could be pressure as well. So anytime a species, a chemical, has its amount increased, okay, the reaction system will attempt to decrease that species. This will cause the other species to experience changes as well. Okay. In this simple example, the other species went up. I don't want to change my eraser example too much, but if I had to take not just an eraser, but a piece of chalk, right? The pile of chalk that I would have to get decreased as well. And if I didn't add extra chalk when I added extra erasers, the poor pile of chalk's really going to suffer, right? Because it was already at its desired equilibrium amount, and now we're going to lower it even further because we added more erasers. Okay, so it's really going to unbalance the whole system, and everything's going to have to shuffle. All right. That's a little more advanced version of it. Okay. Now, so another way of saying this, other language we might use for this, is that the system shifted away from the chemical that we added. We added reactant, and the system shifted away or towards the products. That's the counteraction, to use up the extra amount that we added. Okay. Now, sometimes we take stuff out of our equilibrium systems. So let's say, I've gotten back to this 4:8 ratio, and now I'm kind of running out of room here, so let me erase one line. But, let's say I remove the 6 and drop this back down to 2. Again, I'm not at equilibrium, right? Okay. Now, I'm at 4:2, and my KEQ is, Q, is too small. So I know I need to move 2 more over to get back to my KEQ value of 2. So again, the Q became too small, and now it, caused the forward reaction to occur. All right. But look what happened here. When we took something away, the system shifted towards it. Right? The system came to its rescue, you might say. Right? We took away some student erasers, so the system says, hey, let's make some more student erasers. Let's counteract what some external factor caused to happen here. All right? That's always the goal, counteract.
When you talk about shifting away and shifting towards, do you mean the part in which it was added to?
Yes. Okay. So we added it to the reactant in the original case, and we shifted away from that side, of the reaction, from the reactant side. Here we took away from the product side, and we've shifted toward the product. Okay. In each case, it's subtle, but in each case, it's the counteraction, the sort of the opposite effect that we have there. Okay.
In membrane, similar questions are asking if it shifts right or left. Is that just the same thing?
Same thing. You just have to rethink. If we shift toward the products, that's right. If we shift away from the reactants, that's also right. Okay? There's just different ways of saying the same thing. Here, shift away from the reactants means you're moving towards the products, right? I could say it either way. Sorry that the English language gives us multiple ways to express the same idea, unfortunately. But yeah, and I'm going to show you in the back of the sheet that I handed out several different ways the question can get asked, so you get used to thinking in all the different ways rather than just one way of answering it. Okay? All right, so let me fill in this last piece that we have here. When we remove a species, the system will shift towards it. To try to replace some, it won't replace all, but some of the lost species. Okay, that's important. In both of these examples, first case, I added 6. In the end, I did not shift all 6 over to the other side, right? I only shifted 4 of the 6 to the product side. And then when I took 6 away, all right, I didn't shift 6 in response. I only shifted 2 that time. Okay, so it's all about the ratio. So both of these are guided by concentration changes. We return to the same KEQ. And that's how we know when the system will stop when it gets back to KEQ. All right. The other type of change that we're going to look at are temperature changes for reactions, and they're a totally different animal. So let's consider them. To understand the effect of a temperature change, right away there's a big difference. We need to know the sign of delta H reaction. We need to know whether the reaction is endothermic or exothermic, because that's telling us how energy plays a role in this chemical reaction that we're looking at. And energy, of course, is connected to temperature. So to understand temperature, you need to know about energy in your reaction. And there are 2 things. It could be a product or it could be a reactant, exothermic or endothermic. All right. So this actually is going to give us 4 possibilities, 4 categories. And I like to divide them into just a big grid here. It's a big 2x2 table here. Across the top, let's put a temperature increase versus a temperature decrease. And the top row will be delta H greater than 0, so an endothermic reaction. And the bottom row will be the case of delta H less than 0. That's our exothermic reaction. Now let's define a generic reaction, like A plus B in equilibrium with C. So really, that means the top row, we can think of it as A plus B plus energy are in equilibrium with C. That's the way I like to think about it. When your reaction is endothermic, energy is part of the reactants. It's there to drive the reactants over there to that product side. On the other hand, the exothermic reactions are like A plus B in equilibrium with C and energy. So the energy is over there on the product side of the reaction. And when we think about it that way, we can, to some extent, use the lesson from the concentration changes to help us figure out what's going to happen. All right? There's a lot of dominoes that have to fall, though. All right? So let's get ready to figure out the different steps that happen here. So if we increase the temperature of this endothermic reaction, if we increase the temperature and we add energy, we've increased the ability to do this reaction, to do the forward reaction. Okay? So the temperature increase increases the rate of the forward reaction. Well, what's that do? The forward reaction then is going to increase the amount of products. And as we consume the reactants A and B, because now we have more energy. Remember those reaction coordinate diagrams? We can push more of our A and B over to that product side. We're going to decrease the amount of reactants. In the shift language, hope that came through pretty clearly, the shift language on the video, all right, we have shifted the system right away from the energy that we added. Okay, so saying the same thing, okay, but using different language to do so. Right? This is going to break the equilibrium constant though. Right? Our equilibrium constant for this is going to be our product amounts divided by our reactant amounts. And we've just figured out that the products are going to increase and the reactants are going to decrease. So this fraction that we're calculating over here, this ratio, is not going to be the same number anymore. How is the new number going to compare? Is it going to be bigger or is it going to be smaller? It's going to be bigger, right? So the big picture lesson of a temperature increase for an endothermic reaction is you make it more product favored, higher equilibrium constant for it. Anybody ever grown cell cultures like an auger or something like that? You generally put those in an incubator, right? Have you ever done an experiment? I don't know if they do the experiment this way or have you do it, where you leave a plate out of the incubator and one plate in the incubator to see the difference or whatever? Okay? So not only will the plate in the incubator go faster, that's a kinetics situation. We know that temperature makes all things faster, but it will also go farther, meaning you'll get more. So even if you leave the plate out of the incubator for extra days, 3 days, 4 days, 5 days, you'll never get as much on that plate as the plate that goes in the incubator, because that process is essentially is an endothermic process, and you're going to push it further to the product side, grow more stuff in the end, all right, than if you left it out. That's one of the reasons you do that. Okay? It's also the reason when we don't want stuff to grow that we decrease its temperature. All right? We're going to go in the opposite direction now. So when we decrease the temperature, this is a little bit different again, but in the shift language, what we've done is we've taken away the ability to do the forward reaction. But we haven't impeded the reverse reaction yet. So I don't know if you've ever been in a car driving down the highway and you're next to another car, and then maybe you or the other car brakes all of a sudden because there's like a police officer or something, right? Okay? All of a sudden this other car, it's still going the same speed, but it looks a lot faster than you if you're the one who slowed down. Okay? So we have two reactions going the same speed. When we turn the temperature down, all of a sudden the forward reaction breaks, slows down. B-R-A-K-E-S. Okay, let's put the brakes on. But the reverse reaction, I'm still going at the same speed. So temporarily it's going to mess up the balance of the piles that we have again. All right? So when we turn the temperature down on our endothermic reaction, we slow down the forward reaction now instead of speeding it up. Okay? So the reverse reaction appears faster. What does that mean? That means that we're going to end up increasing the reactant amounts and decreasing the product amounts. So now our numerator gets smaller and our denominator gets bigger, so our equilibrium constant decreases. All right? And we've made the system more reactant favored. We've shifted it left. Okay? The reverse reaction is the favorable reaction at this time. All right? Those are three different ways we can say that same outcome. All right? Any questions on that? All right, let's look at exothermic reactions now. Pretty much everything just flip-flops, okay? Exothermic case, our energy is now on the product side. So if we increase the temperature, we're not increasing the ability to do the forward reaction, we're increasing the ability to do the reverse reaction, okay? So now our two cars are going along, and all of a sudden one of them does speed up. It's not that one has slowed down. Adding temperature allows the one reaction to speed up. And it's the reverse reaction, okay? Reverse reaction speeds up, or I guess we could say increase the rate of the reverse reaction, but okay. What that means is we're going to increase the amount of reactants, because that's what the reverse reaction does. It makes reactants. Okay, so we're going to end up increasing the amount of reactants at the expense of the products, decreasing the amount of the products. And we're going to see a decrease in KEQ. So the system is now more reactant favored. All right. So reactions that are exothermic, we often try to put them in a cool environment then. Right? Otherwise, they're going to sort of kill themselves off. All right? They're going to die out. And that's the origin of using a cooling system, for example, in your car. Your car has this extremely exothermic reaction when octane combines with oxygen to produce carbon dioxide and water vapor. Right? And a whole lot of energy. If that energy is just left sitting here, the temperature builds up, builds up, builds up. And it's going to decrease the amount of the forward reaction that can happen. So your engine will be less efficient then. It won't want to convert every octane molecule into carbon dioxide and water. So what do? Put a cooling system in, you pump that energy away. You take it away and you trick the reaction into happening more efficiently by cooling it down, in other words. All right? So you'd be in this box here. Temperature decrease. So now what happens when we decrease the temperature is we slow down the reverse reaction, because again, energy is used in the reverse reaction. So the forward reaction appears faster. Okay. What does that mean? That we're going to increase the amount of products, decrease the amount of reactants, and when that happens, we see a net KEQ increase. So cooling exothermic reactions will give you a more product-favored outcome. And you get more, if that's what you're trying to make, your products, you get more by cooling the system down. All right, let's try to put this into a sort of a real example now, some practical consideration here. We've seen this reaction before when we were studying heterogeneous equilibria and writing their constants. So calcium carbonate in equilibrium with calcium oxide solid and carbon dioxide gas. What I need to add now is a new piece of information. What is the delta H of this reaction? So it's positive 174 kilojoules. So it's an endothermic reaction. All right? I'm going to ask a few questions to model the sort of the different ways that they can be asked. All right. And again, mastering, which we heard somebody ask about, asks them really in just one way. All right. But there are multiple ways you could really ask the same question. All right. So how will the pressure of CO2 change if we increase the temperature? Okay. Now, a different way of asking that exact same question would be, which side becomes more favored if we increase the temperature? It really is the same question, to be honest, all right? Or how does the system shift, meaning left or right, if we increase the temperature? They're all really the same question, okay? All right? Another question, let's say, how will, what did I do last, just trying to remember the way I asked it last class so that it comes across as a different question. All right. Yeah, oh yeah, that's what I'm gonna do. Which side, okay, becomes favored if we add some CO2 to the system? Okay, so there's a question where we're looking at the sides rather than a specific chemical. Okay. And what happens, that's the most general way rather than sort of, pushing you into a particular line of thinking like which side or what chemical. Let's just say more generally, what happens if we add some CaCO3 to the system? I poorly spaced my writing, sorry. All right, so first question, how's the amount, the pressure of carbon dioxide going to change if we increase the temperature? So this reaction is endothermic, first thing I want to think about. Temperature increase drives the forward reaction. Okay, so the temperature increase favors, we would say, the forward reaction. The result of favoring as the forward reaction is we're going to increase the amount of the products, one of which is CO2. Therefore, the pressure of CO2 will increase. That's the domino effect, right? Okay, that's essentially this box right here. All right, we raise the temperature, we're going to speed up the forward part of the reaction here. The forward reaction makes the carbon dioxide, the product, and therefore we're going to have more carbon dioxide, and naturally its pressure is going to be higher. Okay. Second question, which side becomes favored if we add some CO2? Well, CO2 is a product. So if we add some CO2, we're going to shift away from it. Right? Because all of a sudden our pile of carbon dioxide is too big. All right? And we want to bring it back down. So to try to decrease the carbon dioxide, we're going to shift away from it, which means the reactant side is favored or becomes favored. Shifts left in the language that I think the Mastering Chem question is going to ask you. All right? So this system now would shift left temporarily to take care of that extra CO2. Right? Last one, what happens if we add some CaCO3? Well, we could start to set down the same path that we did in this previous one. CaCO3 is a reactant, so we should shift away from it. But CaCO3 is a solid. Right? The equilibrium constant for this reaction, Kc, does not rely on that. Remember, we learned to ignore solids and liquids in writing the equilibrium constant? We ignore them and their effect on equilibria then altogether. And so what happens if we add some CaCO3? No change. No effect on the equilibrium, actually. The only way it would change is if we took all of it away. Okay? If we took all of the calcium carbonate away, then the system would completely throw the brakes on and turn left and start to make some calcium carbonate. Okay?